So what have we done? We decided that we wanted to define something we're calling the exponent function, and we came up with three properties that we'd like this thing to satisfy. The first two were sort of exponent-like properties, and the third one was a random property that we put in order to try and nail down the definition of this exponent function. So let's see that we've succeeded in doing that. Let's see that these properties together do nail down the definition of exp of x. So what I'm going to try and do is write the exponent function of x as a power series. This is something that mathematicians are very fond of doing. So what does it mean? It means I'm going to write this as an infinite sum of terms. So this is going to look like an infinitely long polynomial. So we need a constant term, which we call a0, an x term, which coefficient has a1, a quadratic term, whose coefficient is x2, a cubic term, whose coefficient is a3, and so on, and these go off to infinity. So what we want to see is that our properties that we required the exponent function to have, in fact, determine what these coefficients are. Okay, so let's think about like property number 4, which we derived from the first three properties. This tells us that the exponent function of x is equal to the first derivative of the exponent function of x. And taking the derivative of a polynomial, even if it's infinitely long, is something that's easy to do. So let's do that. Well, a0 is constant, so when I differentiate that, I just get 0. a1x is a linear term. When I differentiate x, I get 1. So just the coefficient a1 is left out in front. a2x squared differentiates to 2a2x. a3x cubed differentiates to 3a3x squared, and then the term I haven't written will differentiate to 4a4x cubed. All right. What about our other properties? So one of the properties was that x of 0 was equal to 1. So we have this. 1 is x of 0. And what is x of 0? Well, if I take x and put it equal to 0, all these terms which have a power of x will disappear, and I'll just be left with the term in the front, which will be a0. So this nails down a0. It tells us that a0 is equal to 1. And now I look at this equality. If a0 is equal to 1, then by matching powers of x, I know that a1 has to be equal to 1, because it's just the constant term in this power series. So we got a0 equals 1. That's going to imply that a1 is also equal to 1. And if a1 is equal to 1, then the coefficient of x on the top line is 1, and the coefficient of x on the bottom line also has to be 1. So that tells me that a2 has to be a half. And if a2 is a half, the coefficient of x squared on the top line is a half. The coefficient of x squared on the bottom line also needs to be a half. So in order to satisfy that, a3 has to be a half times a third. So the third will cancel with the 3 and just give me a half. So a3 is this. And similarly, if I look at the coefficient of x cubed, that's going to tell me that a to the fourth, a4 rather, is equal to 1 over 2 times 3 times 4. And you can express, and so on. And you can express these coefficients, these ai's, in compact notation by writing ai is equal to 1 over I factorial. And you can express the whole power series in compact notation then, if you like as well. So this is going to be the sum from I equals 0 to infinity x to the I divided by I factorial. And so this shows that those properties that we required the exponent function to have really do nail down the exponent function. And now we've got this, we're set to answer our motivational question, which is what do we mean by 2 to the power root 2? Okay, so now we've got a well-defined function, the exponential function of x, and we can use this to answer our motivational question, which is what do we mean by 2 raised to the power root 2, or by any number raised to the power an irrational number. First of all, we're going to need the inverse function of exponential, which is known as the logarithm, or the natural logarithm. So we're not going to need to know much about it for this talk, except that it is an inverse. So the exponential function looks like this. It passes through the point 0, 1. And to get the inverse function, all we do is reflect this graph in the line y equals x. So this is the function y is the exponential function of x. And the inverse function is y is log of x. Sometimes you'll write it as ln of x, where the n stands for natural. So you have log to different bases. Normally at university you don't have log to different bases, so you'll see this notation more often. All right, and the point about these two functions really for us is that they're inverses. What does that mean? It means that exponential function composed with the log function is the identity, and vice versa. The log function composed with the exponential function is the identity. Right, and now that's it. Now we're ready to look at 2 to the power root 2. So, of course, I'm hesitant to write this because this doesn't make sense, right, for us yet. But I'm going to do some manipulations that seem like they make sense, and we're going to arrive at something that does in fact make sense. And that last thing is what we're going to take to be the definition of this number. Okay. So what is this? First of all, I'm going to express 2 using the fact that logarithm is the inverse of exponential. So this is the exponential function applied to the logarithm function of 2, right? And all that raised to the power root 2, whatever that means. And we're thinking of the exponential function as being something like a number raised to a power, and we call that number e. So I can write this as e to the power log 2, and this is all raised to the power root 2. Again, you know, these things don't really make sense to us yet, but we're getting there. And then I know how exponents are meant to work. So I'm meant to get e to the power root 2 times log of 2. And this now does make sense, because e to the power is really shorthand for us for saying the exponential function. This is the exponential function of root 2 times log 2. And now we've arrived at something that definitely makes sense, because the exponential function we've defined explicitly in terms of that power series, and the logarithm function we've also defined explicitly as the inverse of the exponential function. And so this is one important application of exponentials and logarithms, and one important motivation for their introduction.